Welcome to Math 2318, Section 4.3. In this particular question 1, we are given three vectors. We want to know if these three vectors form a basis for R3. So, put them in a matrix A, and let's see what do we see about this matrix. Well, the matrix A has a pivot position in each of its positions. And so by the invertible matrix theorem, the columns are linearly independent. So those three vectors are linearly independent. They span all of R3, and therefore the columns will form a basis. So fairly straightforward. All right, what about question 2? Again, we're given three vectors. We want to know, do these form a basis? Are they linearly independent? What's going on? So, form matrix A by putting B1, B2, B3 in columns. We do our row operations to see what we can see. And again, we get a pivot position in each of the three columns. Therefore, they are linearly independent, they do span, and they are therefore form a basis. All right, in question 3, we are given this particular matrix. We'd like to figure out, well, what is a basis for the null space of this matrix? All right, so I form the matrix. I'm trying to figure out what's going on if I look at AX equals 0. All right, so we form that particular matrix. I now do some row operations. I'm going to use this one to make a 0 under it. All right, at that point I notice that I can divide row 3 through by minus 13. And once I do that, I see that row 2 and row 3 are exactly the same. All right, so I can make a row of zeros. At that point, well, what do we have? Well, we've got basically x2 is 2x3 minus 4x4. So x4 is free, x3 is free, and x1 is also a combination of x3 and x4. All right, so when I look at that, I can form this particular vector. And now I'm going to split off all the things that have x3 in it and the pieces that have x4. So let's see, x3, I've got a 5, a 2, a 1. There's no x3 in it, so 0. The x4 pieces, I've got minus 2, minus 4, nothing from x4, so 0 and a 1. And therefore, we see the combination of all vectors is a combination of these two vectors, and so there is our basis for the null space of that matrix. All right, in question 4, we have an equation for a plane in R3. All right, so this particular plane, I'm looking for a collection of vectors that would span and be linearly independent for this plane. And so one of the ways of doing this is to consider this as a single equation, 1 minus 2, 5, 0, which means z is free, y is free, and x is a combination of y and z. So put all that together. And so now if I split off the pieces that have y in it and z in it, all right, so the y parts, I've got a 2, 1, no y's. For the z piece, -5, no z's, and a 1. So a basis for all the vectors that live in that plane have to be linear combinations of these two vectors. All right, in question 5, we are given three vectors, v1, v2, v3, and h is spanned by these three vectors. Now, supposing we know there is a relationship between v1, v2, v3, and I want to find a basis for h. Well, by looking at this, I could solve for v1, v2, or v3. They want us to find one basis. There's lots of them because I could consider v3 is a combination of v1 and v2, which means I've got a basis that looks like this. I could find that v2 is a combination of v1 and v3, or v1 is a combination of v2 and 3. So they just want one basis. I could generate several. All right, in question 6, we have a vector space, and in this case, it's a vector space of functions. And this vector space consists of all combinations of cosine omega t and sine omega t. So therefore, the cosine and the sine form a basis for that particular vector space of functions because it has all possible linear combinations. And in question 7, we have a circuit. This essentially comes from differential equations, and we get a solution which looks like V of t for voltage is e to the minus bt times this combination C1 plus C2. And so if you spread this out, you see that V of t is a linear combination, C1 and C2, of these two particular function sets. And so they do form a basis for all voltage solutions for this problem.